Hello, everyone. Thanks for coming. Let me just give you a little background information, and then I'll get right into it. I'm not actually using slides today. I'm going to just work in the REPL. Yeah, you can see my contact information on the right if you want to follow up. Like Dean Wampler on Twitter. I do work for Domino Data Lab. It's a data science platform. It's kind of sort of like an IDE for data scientists. It kind of makes it a lot easier for them to do their work. We do write most of what we do in Scala. We do have some openings. Might even be hiring in the EU as well as across the US. So check out our webpage if you're interested in finding out about that. I'm working on the third edition of Programming Scala, the O'Reilly book, and it's all about Scala 3, although it does talk about Scala 2, where you'll need to be able to learn both if you're working with Scala, and it's designed for beginners, but also tries to catch up experienced people like us in Scala 3 stuff. This link, programming-scala.org, it actually has links to other things that you might find interesting. I've been doing a blog series about Scala 3 features. The code I'm going to go through is already online. It's in the synopsis of Scala 3 changes. I'll show you what it looks like in just a second. And you can even get the book's code examples if you want. They're completely open source, although they're poorly commented because you're supposed to read the book to understand the code. So they're not great in that way as far as commented code, if you believe in comments for code. So we won't get into that. But anyway, so this is the blog series I mentioned on Medium. That's the other link here on the right. And also this bottom link, the Dotty documentation is quite good, I think, for the most part. It's really where I learned quite a lot about Scala 3, so I recommend looking at that. This page is the Scala book code examples, but as I said, you can get to that from the programming-scala.org site. And this is the summary page that I mentioned that talks about Scala 3 features. It's also on my vanity website. You can even find really old crap about aspect-oriented programming if you really want to go old school. But mostly we're going to talk about contextual abstractions today. So let me now go over and get to the code. I'm going to make this a little smaller. Hopefully it's still readable. And I'll bring up the REPL. Okay. So I'm running, I'm actually running the SBT build console for the code examples for the book. Shameless plug, but I'm mostly just going to cut and paste from the editor window on the right into the stuff on the left to show you how things work. All right, let's begin then. So one of the most interesting features that it really cuts down a lot of boilerplate as well as provides some performance benefits is the addition of extension methods in Scala 3. You might recall this famous example of using an implicit conversion to an arrow assoc object so that we can write A arrow B and create a pair, a tuple. Well, now we can do this much more easily with this code. Let's paste that over, see how that works. And then if I try like, 1 to 1 or 2, and actually I used tilde, so I did shadow the original, then I get a pair back. So it's tilde arrow. So what do we got here? We've got the ability now to very concisely say what we want, which is we want to add a method to a type without going through kind of this ceremony of converting it to something else, and that something else has the method we want, which was arrow. So a couple of things going on here in this declaration for this extension method. First of all, there's this new annotation called target name, and I'm using that here because I'm using an operator syntax. Target name actually lets me specify the name that the compiler will use when it generates bytecode. So I could actually call this thing with arrow 2 from Java code if I wanted to use it that way. Although I cannot actually call it that way from Scala code. I'd have to use the tilde greater than sign. A couple other things about the syntax here. Notice how it's declared. We say extension, and then all of the type parameters we're going to need. This is a slightly different thing from, compare it to arrow assoc, where at the type level, I just parameterized with A, the input type, if you will. And then the actual method took another type parameter for the thing that I was passing in, which would be the right-hand side of the pair. With extension methods, you put all the type parameters up front, and then you put this argument list for the thing that you're actually extending, which is that A type, the left-hand type. Then the target name, and I could also do this a little bit that's easier to read. And now this new method takes an argument B returns a tuple as sum. So it looks pretty normal. One thing I'd like you to look at, though, is look at how the REPL represents the signature of this method that I just declared. It's actually a 2-argument list method, where the first argument list is the type I'm extending. The second one is the argument for this method, and then the return type. So that's extension methods, and we'll see a few more examples as we go. It's a good example of a general principle, especially in the context of context abstractions, but I think in general with Scala 3 was try to add constructs that are more obviously about their intention, what you're trying to accomplish, and a little bit less emphasis on structures that are mechanisms that are very general and can do a lot of things, but you have to learn this idiomatic way of using them to accomplish something. We get so accustomed to using an implicit class to effectively create an extension method, but it's actually a bit of a strange thing if you think about it. You're coming at it from a beginner. It's more obvious, well, to some level obvious, that we're just extending a type with a new method rather than doing some implicit conversion behind the scenes, and then that's calling some object.
Dean,
yes.
I'm really sorry to interrupt you. I'm just being told, could you just move, I think you just need to move your screen up a tiny little bit. Apparently there's a something covering it. I think, are you able to just move your screen up a little bit, or your tab?
Yeah. Like this, or do you mean the, or the actual stuff on the screen?
I think the actual, yeah, like the actual,
Let's do this then. I'm gonna, no, that's not what I wanted. I'll just make these shorter. I can get to them. I'll do it this way.
That helps.
Hopefully this will be a little better.
Yeah.
And I'll just, on the right-hand side, I'll just make sure I keep scrolling.
Oh, thank you, Dean. Thank you.
Hopefully that's all right. Thanks for letting me know.
No worries.
Okay. What else about this? We can actually add several methods if we wanted here, and I'll show a few examples of that. But let's go on to type classes, which is the new Scala 3 way of defining type classes. Again, we used to do implicit conversions to classes. Now we'll do something that's a little bit more formalized in a sense. I think I was finishing up on, well, anyway, making the point that it's kind of, we get used to doing this idiomatic way in Scala 2 of creating an implicit conversion, which means an allocation that is kind of wasted. Whereas now we've got this more direct method. It's easier to understand if you're new, but it also is a little bit more efficient at runtime. All right, let's talk about how type classes would look. And typically you'd start with a trait that defines some abstraction. And in this case, they're going to do basically semigroup and monoid. Now, if you don't know what those terms mean, they're category theory. They're really not category theory terms, they're actually algebraic notation, but it's really an abstraction for addition. So the semigroup adds the addition operator, and I'm going to define two methods, one called combine and one that's the Darth Vader spaceship operator. And then the monoid just adds the unit value, like 0 if you're doing integer of numbers, 1 if you're doing multiplication, and so forth. So let's define these two traits, and we'll mostly just work with monoid. So now I have this sense of an abstraction over addition, and I want to add that now to things like strings and integers and so forth. And the way we do that is declare what used to be an implicit value, but now is called a given instance. So let's do that for string and integer. And then I'm going to come back and describe a little bit more about what's going on here. So notice we've declared two objects, and they're named string monoid and int monoid. Let me go back up to the trait for a second, the two traits. And what you'll notice is I've declared these methods in a slightly different way, and I've also used a keyword you probably haven't seen before, unless maybe you went to, no, actually Josh didn't mention this. If you went to Josh's talk earlier, it was, he talked about inline, different than infix, also a very good talk. Okay. First of all, I'm using extension methods here. So whatever trait or whatever things I'm going to apply this type class to, they'll be treated as extension methods. But notice that I didn't declare unit as an extension method. And the reason is that unit will actually be an object method. I only need one unit value for any given type class instance. If it's the string monoid, the unit value is going to be the empty string. If it's integer, it's just going to be 0 for addition, anyways, the way I defined it. Whereas these extension methods are instance methods that I want on the instance. Now this infix keyword is a new keyword, and you may recall that up here that was it was different. Anyway, if I want to use combine as an operator, this is another Scala 3 feature. They're actually trying to encourage you not to get carried away with using alphanumeric methods in infix notation, unless you really intend that to be the case. Because sometimes it causes confusion for beginners. You can cause parsing ambiguities. But if I really want to use combine as an operator, then I just declare it infix, and that allows me to do it. And once again, I'm using target name as well to define a name in the JVM bytecode for this operator that I've defined. Otherwise, these are pretty much the same as what you would expect. I'm actually never going to need to implement this Darth Vader operator. I'll just call combine here. So the only thing I'll ever actually implement is combine. And that's what I did down here. So once again, I did extension S string, and then I put infix on the same line and so forth. I could have made this on another line if I wanted, like so. Even though this method combine was declared infix in the trait, I still have to use the infix keyword here for it to take effect. So it's kind of an interesting difference to be aware of. But otherwise, once again, I made the extensions instance methods. This is probably better indentation. And then I also used a regular object method. Again, these are objects on the left-hand side over here on the REPL. And now I have a unit on object that I can call. So let's actually try these. So here's, let's do it with string monoid first. So notice I can add strings in the usual way. I could have used plus, of course, and I put in just some samples of the kind of algebraic properties. Associativity in this case should be obeyed, not necessarily commutativity, especially for strings. I can use combine because I declared it infix, and I can also reference the monoid unit when I wanted just to add with the unit. And similarly for integers. That should just work. Okay. Well, it's kind of stupid to define separate type class instances for each of the numeric types because we have this notion of numeric. So I ought to be able to define this generically for all types. And here's how you do a given instance with a type parameter, in this case t, and the usual kind of context bound, t colon numeric. And I wrote the colon with a space in front of it. I always just got in the habit, but there's nothing significant about that. So this is the same thing. Now notice that I've actually defined a class because there's still a type parameter t floating around. It's actually a class that'll get instantiated on a per instance basis when I actually apply it to a particular type of numeric thing. A couple of other things. Josh mentioned that there's a new method called summon. It's really identical to implicitly. Because implicit is now kind of the old mechanism that will be slowly deprecated over subsequent releases of Scala. There's a new method called implicitly. So that's how I get the unit value. In this case, I need to get the corresponding numeric.0 is what I need. And then the extension method looks pretty much like what we're used to. Once again, I have to use the summon method because I don't have a name for my numeric. And when I've done this, now I can use these the same stuff for things like big decimals and doubles and so forth. Notice that in this first example where I use the unit, because I had big decimal on the left, it can actually infer the type on the right. That doesn't work here when I put the unit on the left because it doesn't know yet what it's going to be on the right. So there I have to say big decimal. Now, there are some other things that we can do with these given instances. And once again, these are going to be the implicit values that show up in implicit clauses. And we'll see what those are in a second. I'm not actually going to paste these in the REPL just so that I'm not already overloading a lot of stuff that's implicit in the REPL, and I'll even have to restart it in a minute. I could write this the usual way where I have a using clause, which is replacing the implicit clause. I'll come back to these details in a little bit. But think of this as like just the implicit keyword for now. Now I've got a name for this implicit value, so I can just reference it directly and I don't have to use summon, but otherwise this is the same. And I can also make these anonymous. Now this is just repeating what we had up here. So what I want you to, the reason I put this in here this way is because it's kind of confusing to read a declaration like this because there's no name here, but all it really is I just remove the name numeric monoid, and now I have an anonymous. If I actually paste this in the REPL, I would have an anonymous given instance for monoid of type T, where T is context bound to be a numeric value. Well, I now have to use summon again, but otherwise, this is how you can actually declare an anonymous given. In fact, this is going to be much more common. The old syntax with implicit vals, we had to give them a name because it was basically like declaring a regular value. But with givens, you can now make them anonymous when you don't need the name. And so you'll see that quite often. And just for completeness, here's how it would also look if I used a regular using clause instead of the context bound type declaration. So, if you forget, if you're trying to look at something like this and it looks like maybe it's supposed to be anonymous, or and you're trying to understand the syntax, just put a name in here, and then hopefully it will kind of make a little bit more sense. But otherwise, it's the same as what we had. There's one last thing I didn't really mention, but notice that we create these things with this with the with keyword, and it's basically we just implement the trait in kind of, it's almost like we're creating an anonymous subclass. By implementing the fields. We'll see another way to do this in a few minutes. Okay, so that's the syntax. It'll take a little getting used to, but I think once again, it goes more towards very intentful programming about what we're trying to accomplish, and less about some core mechanism that you have to learn how to use idiomatically. However, implicit conversions are still useful in some cases, but they won't be as common. So here I contrived an example where I have some domain types. I'm going to do some finance application, HR, and I need types for, American currency, percentage, like deduction for taxes, and then computing salary. But I'd also like to give users the ability to just put in like floating point numbers here, and they'll just automatically be converted to dollars and percentage and so forth. So we import implicit conversions, and there's a new type called conversion. It really is sort of very much like a function type that goes from left to right or double to dollars in this case. And this syntax I'm showing you, I'm saying given conversion equals is actually a shorthand for defining an apply method, which is actually what this is doing. So I'm defining an apply method like a function literal. In fact, it looks like a function literal on the right because it basically is. And that's letting me do this implicit conversion for the specific use case that I have in mind. And now, actually, if you look at the values on the left, what you'll notice is these are lazy values. So they're not even constructed until we need them in case they're expensive, but they'll only be constructed once. And so if we use these, and there's another little trick you'll see in this code example, this new to Scala 3. So I could just pass in floating point numbers, but I get nicely formatted, output because dollars and percentage, do the thing I want with the various characters. Notice this floating point number, you can now embed underscores in long numbers, floats, integers, and so forth. You don't actually have to do every third. You can put them in every other if you want. It doesn't care. The compiler just strips them out, but it's a way to write things a little bit more in a more readable way. Okay, so we talked about now how you create these, what used to be called implicit values, and you can still do that if you want for a while. How do you actually use them in functions? Well, I came up with this kind of contrived class that's a sortable sequence, although sequence itself is already sortable. So I'm just kind of wrapping existing behavior. This is maybe a bit hard to read. Let me spread this out a bit so it doesn't wrap as much. All right. So all I'm really doing is wrapping sortable sequence, but what I'm really trying to do is show you the different ways you could declare these things where you have some sort of implicit argument, in this case, an ordering. And the first two are the ones we've used forever in Scala 2, where there's an implicit ordering object that I pass, or I use the usual context-bound syntax like this. In Scala 3 now, we would use the using keyword, and it could also be a named value if we want. So you hear well, notice what I'm doing actually when I pass explicitly the implicit value to the underlying sequence sort method, sort by method. Now you're supposed to use the using keyword. And I say you're supposed to because for Scala 3.0, you'll be allowed to omit this so we don't break whole code. but eventually it'll be required that if you pass the value explicitly, you use the using keyword. And that's going to have some very useful benefits that we'll see in just a minute for disambiguating possible scenarios. So if I'm passing the value explicitly, I'll say using O. In this case, where I'm now can pass values anonymously using without a name, then I use summon with the using clause, and then the usual context-bound syntax where I still have to use summing when I pass these values. Now, so I could go through these examples and just delete these using keywords, and it would compile fine with Scala 3, but in 3.1 and so forth, it'll probably trigger a warning if not an error. I'm not even going to show an example of using this as kind of basically trivial wrapping of sequence, but just wanted to show the syntax, and in particular, the new ability to make these things anonymous when you don't necessarily want to pass a name. Let's talk about then why this is useful for disambiguation. You know, it used to be in Scala 2, you really could only have like one implicit argument list, and it had to be the last list in the definition of a method. But now with these using keywords, and especially at the use site where you actually call the method, we can do things like have multiple using parameter lists if we want. Or we can even have them in the middle. This is kind of a bizarre thing to do, but you can actually put them in the middle if you want, and then have like another regular parameter list. Not necessarily recommending you do this, but just making the point that this is now a possibility. And actually, there is a few kind of small scenarios of where it disambiguates things, like an apply method that doesn't take arguments except for an implicit. And I won't get into details here, but there are some nice features that this provides that eliminate some ambiguities that you can run into. Okay, so a lot going on here, but basically I'm just passing like a first argument, a string, and then either one or two using clauses, and then here I'm actually passing a regular parameter list that I'll have to provide. I declared a couple of given instances of these case classes that I created just for examples, and now I can try different combinations of calling these methods. So in the first case, F1B, I just used two implicit parameters, and the second example, I just passed them explicitly using the new using keyword. And then in the F2 example, I did have to provide U2S, but notice that this is not ambiguous, this last one, because it knows that there has to be a regular parameter list, and it infers that, okay, well, he didn't use the using keyword, so that means I'm going to use the implicit value or the given value for the second argument list. I didn't quite say that right, because I just said a minute ago that using the keyword is optional, but the compiler did infer the right behavior just from the types. Actually, something you may not know, I don't know if Bill mentioned this in his talk about the type system. It used to be in Scala 2, it would only infer types, like unique type signatures up to the first argument list. It now goes all the way across. Actually, I'm not sure about the return value, but it actually does infer uniqueness across, or the signature of the method across all of the parameter lists, not just the first one now, when you're trying to define unique methods. So these are indeed, well, they're named differently, but I could actually use the same name and they would be considered unique. Okay, so that's kind of a crazy example, but something you can do. Just for completeness, you can also make these context parameters. That's sort of the name that's used for these the values like U1 here and so forth. That they're called context parameters. You can also make them by name if you want, and that gives you all the usual benefits of by name parameters. So I created a sketch here of maybe something that's a database interface where I've got something that can do transactions. I'm going to pass an implicit or given connection manager, and then I want this function or this method to do transactions. And oh yeah, right, I should, let me change that. This should be that. All right, let me try that again. All right. Oh, yeah, there's another mistake here. I basically condensed a longer example I had, so I didn't define status, but I think you get the point. If you just look at the example over here, what I'm doing is, the key thing is I'm passing a by name parameter for the connection manager, which means that it will be, constructed not only lazily, but it'll actually only be evaluated, whatever expression I used, inside my do transaction. So if this is an expensive process, then it's only going to be evaluated on demand when I need it. Okay, so a slight advantage there of using by name parameters versus regular named parameters, or by value parameters rather. Now, imports are also changing in a useful way. So one of the problems with doing like a __ import that we've done in Scala 2 forever is that it also pulls in whatever implicits were defined in scope. And maybe that's not what you want. Maybe you want more control over when you pull in implicits or not. So the behavior that we'll get to, again, a lot of this stuff is going to go over several releases to avoid breaking too many things at once, is that when you do an implicit _, it will only import everything that isn't declared implicit or given in the code. And if you want all of the implicits or givens, then you'll do .given, and that will bring all of them in. So this third example actually does bring in everything as it would have been, or as it was in Scala 2. Now, if you want a particular given, then this is, I think, just maybe slightly confusing until you understand what's going on. These qualified givens are actually by type. So I can't say given, here I declared 2 givens for type C1, there's a _C1, and then C2 and C2. If I want to pull in just the C1, it wouldn't be given and then lowercase c1. That actually doesn't work. In that case, I just do a regular import, just given dot, or rather import o1 dot lowercase c1. But if I don't care about the name, and normally I wouldn't, I just want to, just give me the given that corresponds to this type, then this is what you use, given with a particular type. So I'll just paste this in to make sure I'm not a liar, that it actually works, even though the last one didn't work. There we go, so that seemed to work. So once again, you'll use given when you actually want to pull in the implicits or givens, and then you can qualify it by type. And if you just want to pull in a particular instance, like execution context.global, you'll just import that the way we always have, with by name. Okay, so how are we doing on time? I've got 15 minutes or so left. Let me go into some more advanced things. I've given you really the basics now. I think what I like about what we've seen so far is, once again, it's more intentional about what you want to do. The type class syntax, I think, is very nice, and the extension method syntax is very concise. The type class syntax, or actually the given syntax, there's a lot that's changed, and if you've been following Scala 3's evolution, they've even tweaked the syntax a few times. But I think in general, once you get used to how it works, and it's pretty nice and concise. I should mention they're about to release RC1 for Scala 3. I'm not sure if Odersky mentioned this in his keynote this morning. I missed it, unfortunately. But it looks like we're going to go back to Java-style stars instead of underscores for imports. I think that's coming in this release candidate. So I'll have to update the example on my website and there's a few other things that are changing as well with the import syntax. Quite controversial, like the braceless syntax I've been using, but I have to say, I'll just mention this in passing, I actually really like the braceless syntax now that I've gotten used to it. It took some getting used to, and I wasn't so convinced at all it was a good idea at the beginning, but now that I'm used to it, I kind of like it. And obviously, since I'm using it, I guess. Okay, let me reset my REPL. And it's because I'm going to do a little bit more with our monoids and semigroups, and so I'm going to just re-import those. It's because I want to throw away the givens that I declared earlier. And I want to talk about something that's a bit subtle, but it's important to understand the difference between the syntax we had before, where I had like given, monoid, with, and then I implemented the methods, and this new thing called an alias givens, where it's actually going to look a little bit more like you might think a traditional declaration would look like, where I say, some value equals, and then new trait, and then here are the methods for the trait. So anonymous subclass. This actually behaves quite a bit differently than the givens that we saw previously. Now, if you recall, when I did like string monoid earlier, I actually got objects out. That was the thing that was created when I declared these givens. these are going to be different. So let me go ahead and define these things that I need. I'll do the import again. And now I've got my two traits in here. So now notice I'm going to create a new numeric monoid, but this time it'll be equal new monoid, and then I'll implement all the stuff. And I've added this println statement because we're going to actually see how often these things are constructed. It's not just going to be one and done anymore. Okay, so now I have my numeric monoid alias given. I'll go ahead and do string as well. And I'm doing string because it doesn't have a type parameter, because if you look at the signature of these things, the numeric monoid is actually a method. So it's going to get called a lot. Whereas the string monoid is now a lazy value. So it'll get constructed once on demand. And that has implications that we'll see now. So if I do the like a double addition, as we saw before, I actually constructed one 4 times, 4 instances of this monoid. So this could have performance implications to be aware of. In fact, it behaved a little bit more like the old implicit conversions, where I instantiated something and then I called my method. So slight disadvantage to this approach. Whereas, because the string monoid is a lazy value, as I said, it's only constructed once and then it just gets reused over and over. So that's something to know about. If it would be very easy to think when you see syntax like this that you're defining a regular given instance, because it kind of looks normalish, right? But it's actually not the normal way. It's an alias of the normal way, I guess. I'm not exactly sure where the alias word came from in this case. But the normal way you'd want to define these given instances would be like string monoid of type blah with, and then the methods that you want to implement. Okay. There's some interesting things about pattern matching in various contexts. So let me define a couple of more types just to provide some implicit values that I'm going to use in a minute. So I'm going to witness the existence of integers and strings. And I'm going to define a method that is taking, a using clause, and it's going to expect, a witness value to be in scope. Now, if I just call that, hopefully you're going to expect that it's going to complain because I haven't actually defined any given instances. And sure enough, it didn't find any. And the error message still says no implicit argument. I assume it'll be changed at some point to no given argument, but whatever. But notice what I can do now with for expressions, and this is generally true about match expressions. I forgot to add this. Let's see if it, yeah. This is kind of the new-ish for loop syntax, if you haven't seen it, or you can use, it's an optional syntax. You can use do. So now what I've done is I actually treated those regular objects I have up here, I put them in a sequence, and then I pattern matched, but I made them given instances within the scope of this for loop. And but only one was in scope at any one time, so that when I called use witness, it just used the one that happened to be in scope. It didn't complain that there were several in scope because only one was ever in scope at any one time. And then it printed the result. And if I go back to use witness, now nothing's in scope again. So that's kind of cool that you can basically use this given keyword to turn like a regular instance into a temporary, if you will, given instance. Josh talked about type class derivation, and I'll just give you a brief sense of it. So, and maybe one of the most interesting ones, and I think this is the only one that's actually implemented in the library, even though the EPFL documentation talks about a few others like show and I forget what the other one is. Also, it uses the word EQ, and equals has sometimes been there. The current name is can equal. So the idea was strict equality, and the documentation page for this is called Multiversal equality. Here's the problem. So we've had in, because of Java conventions, we've always defined the equals method to be, basically this. I'll just type it in. It's something like def equals, other, any ref, Boolean, on some type, on some type T or whatever. But it's kind of crazy to be comparing across types when presumably, except in rare cases, it'll always be false. So the idea with multiversal equality is you can define these sort of mini verses, if you will, where type equality is allowed, but otherwise the compiler won't even let you compare two things that are never going to be equal. So that's the idea with strict equality. It is a language feature, so you can either import it with a command line flag or in the usual import way. It is quite restrictive, so it'll make things like equals equals tests fail that maybe you normally worked fine and you were happy with. So I don't use it globally yet myself. But let's just see an example. I'll declare a little tree type to represent trees of branches and leaves, and I'll have it derive can equal, which means the compiler will automatically implement this type class for me. Or you'll create a type class instance for me that supports the can equal functionality. And what that basically does is it's going to let me compare only instances of trees where the T type is the same. And I'm not going to take the time to go into the details. The Dottie documentation has a nice explanation for what this actually does behind the scenes, and it tells you how you can implement your own support for derives with your own type classes. All right, once I've done that, I'm assuming you've seen the enum syntax before, but if this is completely confusing, just think of this as a sealed abstract trait called tree, and then branch and leaf are two case classes that implement tree, and that's basically the same sort of thing. But I do have to import branch and leaf. They are nested underneath tree if I'm going to use them. So now I'm going to create a couple of these. I'll create a couple of leaves, and then I'll create a tree that has a couple of branches and leaves. But notice that one of them is a tree of strings and the other is a tree of integers. Now let's try this. L1 should equal L1, and that's fine because they're the same tree types. But I'm not even allowed to compile this expression. This is a compile error. It's not even like an assertion failure. The assertion should pass, right? If I could compile this because the integer tree is not equal to the string tree. But they are not allowed to be compared. So I get much stricter type checking, or when in terms of equality checking. And the reason it fails is because there's no can equal that's in scope that can match this. So just to finish out here, let me, so I just did that one. These are of the B and L1 are of the same type. They're both strings, and I can certainly compare the two branches. That all works fine. What I'm actually doing though is looking for, let's do these one at a time. I'm looking for a can equal in scope that is synthesized by the compiler that lets me compare tree of string to tree of string. That's trivially okay. I use sum and define that thing in scope, and it returns that it found one and it's happy. Same is true for integer trees. But if I tried this one, this is going to fail. So it can't find, something in scope, but can equal. Now, if I really wanted to be able to compare these two different kinds of trees, I could actually add that ability with this feature, but it's something I have to take the initiative to do. So multiversal equality is the key here, and the idea is to make your equality tests much more sensible in terms of typing. Okay, running near the end, actually, I think this might be the last feature, and that is context functions. I find this feature slightly confusing to understand, but it's got a lot of powerful capabilities. So what I'm going to do is I'm going to wrap futures, not functors. So I'll do the usual imports for Scala concurrent stuff. And now, oops, I didn't quite get that right. I missed some things here. There we go. So that's what I really wanted to do. So two things that I've defined in this object. Let me look at the apply method first. This is sort of like future.apply. Actually, I'll come back to it. Let me do the type alias. I'm defining this type alias executable of T, and that's equal to this new thing, which is a context function. Notice this new way of indicating a context function. What is a context function? It's a function that only takes implicit or given values. In this case, an execution context like the usual global one that we've all used. But it gets its own special syntax. And now notice how apply looks compared to future.apply, which is in the comment above. In future.apply, I have this implicit argument, an execution context, but I don't have that second argument list in apply. Instead, what I have is I say that it's going to return one of these executables wrapping a future of t, and then I just turn around and return future.apply body. So this is where it gets a little confusing, I think. I said I'm returning one of these, but actually all I really return is a future. So how does this actually work? Well, basically what it does, I can just try it here. Let's do that quickly, and then I'll explain what it's doing. All right, so it just did the usual future stuff. So what is actually happening? Well, when I return the future here, it's actually going to get wrapped in an execution context implicit value that will then it'll get applied automatically, this function, and then that will return the future that I want. So I find it a little convoluted what's going on here, and I didn't actually explain it that well, but it's a way of writing things a little bit more concisely. The example here really isn't showing the power of this thing. If you go to the Dotty documentation for this feature, you'll see a pretty interesting example where they use it to build little mini DSLs for things like JSON and so forth that are much more concise than they would be if you use the usual syntax with implicit arguments. So anyway, this is kind of a feature that I'm still getting my head around, but the idea is that it kind of basically carries a little bit more weight for you with a declaration like this means that you do a lot less of stuff like this is kind of what happens. Okay, we're pretty much near the end of time, all time, history. The sun's about to go red giant on us, although in Chicago it's snowing like mad today, so maybe not. Anyway, I appreciate your time, and I'm happy to take a few questions now, or we can just flip over to the spatial chat.